So we are looking at chapter 14 and we're only focusing on section 4, and we're going to be talking about concentration of solutions. So the biggest equation we're going to need in this chapter, which will be provided for you on your equation page, is the molarity equation. It is molarity and it is moles divided by liters. And the units for molarity is molar or capital M. Another way that you may see the unit is actually the mole divided by liter unit as well. So you can either use mole divided by liter or capital M, not lowercase m. We're going to be looking at weight percentages, which means you would do the weight of the part divided by the weight of the whole, multiply by 100 if you wanted to get a weight percentage, and a volume percentage, which is similar, the volume of the component you're looking at divided by the volume of the entire thing times 100. Okay? So the first thing we want to talk about is how do you make a solution? And remember, a solution is actually a homogeneous mixture, which means the component is equally distributed throughout the solution and you cannot tell the difference inside. So first, we're always going to weigh out the amount that we're going to calculate, which we're going to learn how to do today. We then add it to a small beaker and we dissolve the solid. A lot of times we're going to use a stir rod to do that. When it is all dissolved, we're going to transfer it to a volumetric flask. And this is a key word you're going to have to know. When making a solution, you have to know that you use a volumetric flask. And this flask is pre-measured for only one volume. So maybe you have a volumetric flask that is only good for maybe 100 milliliters, for example, and that has a etching right here that will tell you when you reach that etching, you are at exactly 100 milliliters. It is the most accurate measurement of a liquid that we have. Okay, so when you make a solution, you have to make it in a volumetric flask. So you pour your solution in, you then fill the rest up with water, and what you want to talk about or make sure you achieve is you want to hit that etched line, which I told you, they call it a scratch mark here, and you want your meniscus of your water to line up with that scratch or etched line, okay? You then go ahead and invert it, so you put a stopper on the top and you mix or invert it up and down. So that's just a little bit of an overview of how you make a solution. Now, how to calculate molarity. So this is our new equation here. Let's remind ourselves of the equation. Molarity equals moles divided by liters. So one thing I want to remind you here is at the bottom, 1 liter is equal to 1,000 milliliters. You will need to know that conversion off the top of your head, and you will be using that a lot. So calculate the molarity. We're looking for molarity of a solution containing 1.4 moles of acetic acid in 250 milliliters of water. All right, so we're going to go ahead and plug this information in. We have molarity, which is what we're searching for. We have 1.4 moles, okay? And then we need to get this value into liters to make sure we can put it on the denominator location of this equation. So I'm going to go ahead and show you a little bit of a conversion, and you may not have to do this once you get better at this, but I do want to demonstrate it to you. So milliliters, you put milliliters on the bottom, you're going to liters. There is 1,000 milliliters in a liter. So you're going to take 250 divided by 1,000. That's going to get you 0.250 liters. So I can then go ahead and fill that up in my spot, 0.250 liters. Okay? When I go ahead and divide that answer, 1.4 divided by 0.250, I end up getting 5.6. And again, my units are big M, or it could be 5.6 moles per liter. Both of these are acceptable, okay? Either way. So let's go ahead and do another problem that takes it one step further here. Calculate the molarity of a solution containing 2 grams of potassium chlorate, and we are given the formula, and it is diluted to a mark of 150 milliliters. So remember, they're probably using a 150 volumetric flask to make this solution. Now our equation still is moles divided by liters. So you can clearly see, I like to always make a game plan here. The milliliters is going to be converted and fit down there, but this 2 grams cannot fit in the mole spot, okay? So we need to go ahead and convert 2 grams into moles before we can put it into the top. All right? Let's go ahead and do that first. I like to do that as a separate step. So I'm going to go ahead and take my 2 grams of my KClO3, and we just did this in the last chapter here, conversions from grams to moles. You are using molar mass of KClO3. You will need to show this step. And then I'm going to add 1 potassium, 1 chlorine, and 3 oxygens to get the molar mass of that. And I got 122.55 grams. Okay, so I just added up the molar mass. So I'm going to take 2 divided by that number, and my answer in moles is 0.0163. Okay, so I kept 3 sig figs there, and that is moles of KCl. So now I am equipped to fill in the top of my equation here. So 0.0163 moles. Now the bottom is the same situation where you go ahead and take your milliliters to your liters, divide by 1,000, move the decimal place over 3 spots, which is maybe a better way for you to remember. 0.150 liters on the bottom. So this took it 1 step further here. We're still going to divide. And my molarity ends up being it is 0.109. And I'm going to use big M, but you could use moles divided by liters as well. Okay? So 1 step further, you cannot use grams in this equation. You have to get it into moles first. All right, now we're going to go backwards. We're still using the same equation, but we're going to approach it from a different angle. So calculate the number of grams of KOH required to prepare 600 milliliters of a 0.450 molarity solution. So when I approach a problem, I like to start off by writing my equation and kind of seeing what I have. So I can clearly see that this 600 mils is probably going to fit down here once I convert it. And this molarity is going to fit here. So this is what I need to solve for. Okay, it's just a plan of attack. I'm going to go ahead and fill that in now. So my molarity is 0.450 molarity, KOH. And I have I'm going to go ahead and convert that just automatically to 600 liters. And you guys know how to do that. And then go ahead and put moles, which is what I'm looking for. Okay, if you prefer X, you're welcome to put an X there. Now to remind you, when you have something in the denominator spot, you can multiply both sides by it to get it out of the denominator spot. So I'm going to go ahead and cancel that side. So my problem really ends up being 0.6 times 0.450. When I go ahead and multiply that, I get a 0.27, which it looks like I possibly cut off a sig fig there when I did the calculation. I do apologize about that. But I end up with 0.27 moles of KOH. Now, this is not the answer though. The answer is asking for the number of grams. I am in moles, so I need to do 1 extra step. I need to take my moles and go to grams. So it's basically the opposite of what we were just doing in the previous problem. So you have to get the molar mass of KOH. If you add 1 K, 1 oxygen, and 1 hydrogen, you get 56.11. Since they are both on the top, I'm going to multiply, and I'm going to get 15.2 grams of KOH. So what does this even mean? This means that if I were asked to make a 0.450 molar solution of KOH and 600 mils of it, I would go over to the balance and weigh 15.2 grams of KOH, dissolve it in that water, and fill it up to the line. Okay? Now, we just talked about molarity. Now we're going to talk about the other big concept in this chapter, which is dilution. Okay? So whenever you dilute something, as you know, you make it less concentrated, right? Usually our universal solvent is water when we are diluting something. So let's say you have very concentrated iced tea, for example, and you want to dilute it a little bit, you would use water, all right? And you'd make it less concentrated. So now we have an equation here that we're going to be utilizing a lot, and it's not a hard equation, but the variables are a little bit confusing. So I want to go ahead and work through those first with you. So M1, V1, M2, V2. To remind you, M is going to be molarity. Okay, and V is going to be volume. Now, molarity has to be in capital M or molarity units, molar units. Volume has some options as long as they are the same. So it could be milliliters, but they both have to be milliliters. It could be liters. They both have to be liters. Or you may even see centimeters cubed, although I doubt it. Okay? So a couple options there. So M1 is your initial solution molarity. Okay? So this is usually the concentrated one, okay? Your volume, okay, is going to be how much volume, and again, that could be in milliliters or liters, you take out of the initial stock. Stock just means solution. Okay, so how much you are taking out, and I will describe this in a moment in the picture form. So that's M1, that's V1. Okay, I'm going to move to a different color here to help us. Now, M2 here is your, I'm going to go ahead and draw an arrow here. M2 is your diluted solution volume. Spelling that wrong here. Diluted solution volume. Okay. Obviously, it's going to be less than M1 because it's diluted. It's going to be a lower molarity. And V2 is your total volume of diluted solution. Okay, the total volume. So let's look at this picture of how to create a dilution, and then we can kind of describe the different components here. So first we have I'm going to make this yellow. This is your M1, your V1. That is your concentrated stock. You see the word stock solution there. That means concentrated. Then you're going to take out, actually, I'm going to make this here like a purplish. You're going to take out a certain volume, and that is right here. Do you see that? And that is going to be your V1 that you're pulling out. So maybe you're pulling out 10 milliliters. Then you're going to take that volume and you are going to transfer it into so from your stock or your concentrated stock, and you're going to put it into now your diluted one, your diluted solution. Okay, so we have that blue solution. I'm going to try to keep this key here. The blue solution that was in your initial, we call that a pipette. You go ahead and put it in your new volumetric flask. And then what you do is you fill up your flask with water. So your diluted solution here, and you are filling the rest up all the way up to this etched line with water. Okay. Now, that whole solution right here, the whole volume of that solution is going to be your V2, okay? So maybe 100 milliliters, whatever the total volume is. And then that's molarity is going to be the M2, all right? So let me just go ahead and put some numbers on these. So this is 1 and this is 2. This is still the same 1 and 2 flasks, 1 and 2, okay? I will also link a video to watch this process as well. All right, so be careful when you are reading the problems when you determine V2. V2 is probably the hardest, and along with V1, the molarities are not all that difficult. And make sure you keep your volumes the same, okay? Let's dive into an example here. So you have, and I find this a lot easier to sometimes visualize when I draw a picture. Now, you may not need to do this forever, but I think it's a good helpful starting point. So I'm starting with 50 mils of this 0.4 molar solution. So please ignore my artistry. It's awful, but this is my concentrated. And there is 50 milliliters of a 0.40 molar solution of NaCl, table salt, right? The chemist dilutes the solution to 1,000 milliliters. So what we're going to have is a new volumetric flask. That's awful, but that's okay. You get the point. And this is my diluted, and this is now 1,000 milliliters. Okay, so you can see the volume change here. Calculate the concentration of the new solution. So we are looking for the new concentration. Concentration is another way to say molarity. Okay, so we're looking for the diluted, which is our M2 concentration. So let's dive into our problem. M1 V1 equals M2 V2. So my M1 is all of this information, and my V1 is this as well. This is M2 and V2 information. Okay, so sometimes you'll see info that say this is all about the concentrated, this is all about the dilute solution. You may want to think of it that way as well. All right, so my molarity of my concentrated is, the problem tells me 0.4 molarity. My volume is 50 milliliters. Now I'm trying to find M2, so I'm going to put that in there. And my second volume is the total volume, which is 1,000 milliliters. Okay, so not too hard once you get it all organized. So when I go ahead, I'm going to multiply these two numbers, get an answer, and then divide by 1,000. Okay, and when I get that, my second molarity of my dilute solution is 0.02. I do agree I cut that off in sig figs, I apologize, but just focusing more on the problem here. So 0.02 molarity is my concentration of my new solution or my dilute solution. Okay? Let's do another problem. We'll go ahead and draw a picture. Calculate the molarity of NaOH from mixing 100 milliliters of 0.2 molarity with 150 milliliters of water. So this is another example where a picture is helpful. So I'm going to go ahead and draw these are more like round bottom flasks, but that's okay. This is my concentrated. This is my dilute. Okay, so we're trying to find the molarity of NaOH from mixing 100 milliliters of 0.2 molarity solution. So looks like I'm starting with 0.20 molarity solution, and it looks like I'm taking out 100 milliliters of it. Okay, so it's going to be going into my new one. But in this one, now I'm going to have 100 milliliters of that initial, but I'm also going to have an additional 150 milliliters of water. So what is my total volume for the dilute solution? 250. So that's why it's so helpful to kind of visualize what's happening here. All right. So I'm going to go ahead and do an equation. M1V1 equals M2V2. My initial molarity here was 0.20. My initial volume I took out. You have to remember that's not total. It's how much you took out. 100. Trying to find M2. And my V2 here is my total volume of the entire thing. Not just the water, not just the solution that you put in. So 250. And again, milliliters. Please, please, please confirm that your units are the same for your volume. This is milliliters, this is milliliters. If they were not the same, you'd have to convert to get them to be the same. So same math here, multiply 0.2 times 100, get an answer, divide by 250, and my answer ends up being 0.08 molarity for my new solution. Okay, a good check is, since it's the dilute, it should be less than the initial molarity, which it is. It's a nice little check to make sure you did it correct. All right, let's talk about molarity of ions. So we're calculating the molarity of a solution containing, let's see here, 9.82 grams of CuCl2, and I gave you the molar mass or the formula weight there to save you some work, and 600 mils of water. Then we need to calculate the molarity of the cation and the anion. Remember, the cation is just the positive ion. Typically, that's the metal. And the anion is the negative ion. And usually, that's the non-metal. So we'll focus on that in a moment. So we are trying to find molarity. My equation for molarity is when I am working with some sort of not moving things from one to another, but just one compound. It's just molarity equals moles over liters. And I have a molarity of what I'm trying to figure out. So I need to go ahead and put in my information. I first have this, but I need to be able to convert it to moles before I can plug it in. So I'm going to go ahead and do a little side equation here. 9.82 grams of CuCl2, grams to moles. Use my provided molar mass, which is nice. Okay. I'm going to take 9.82 divided by 134, and I get 0.0730 moles of the CuCl2. So that's actually going to go on the top here, 0.0730 moles. And now this 600 mils of water, I need to convert to liters. We did that in the prior slides. If you want to, oh, excuse me, this is liters here. You can check that out if you need that. So my molarity of my total solution is when I divide these, and I end up getting 0.122 molarity of CuCl2. So that answer is my total solution. Okay. Now, the question asks you of the cation and the anion. So what we're going to do is we need to see how many there are of each. This is the cation. This is the anion. Remember, I told you cation is a positive ion, anion is the negative. So the cation is always first. The anion is always second because it's always a positive and then a negative charge coming together. So what we're going to do is if we see, how many coppers do we see here? We see 1 copper. And we see 2 chlorines, obviously because of this little subscript 2. So I have a little tip. Instead of doing a mole ratio for this, you can just use logic. So if I have 1 copper, okay, this actually ends up just being multiplied by 1. So therefore our answer for our cation is 0.122 molarity. Now, because this chlorine has a 2 here, we have to take this molarity and multiply by 2 because there's 2 sets of chlorine with that molarity. So basically, you just multiply by the subscript. And so when I take 0.122 times 2, I get 0.243 molarity. Okay? And so the cation in this case is the copper plus 2. You want it, you don't need to write this, but I'm just kind of showing you in the chlorine a -1. Since there's 2 chlorines, we have to multiply it by 2. Since there's 1 copper, we can keep it the same as the molarity. All right, now, last sort of way we're going to use molarity and dilution is in stoichiometry. So we have 2 more final examples to finish us up. So what we have going on here is how many grams of silver chloride can be precipitated, which just means that it's producing a solid. You can see that right here, the little S, by adding sufficient silver nitrate to react with 150 mils of barium chloride. So a lot of information here. When I'm dealing with a lot of information, I like to go ahead and organize my information to help me get a clearer picture of what I'm going to do. So let's go ahead and do that first. How many grams? So this is what I'm looking for. How many grams of silver chloride? So I'm looking for this in grams. Can be precipitated by adding sufficient silver nitrate. Well, sufficient silver nitrate doesn't really tell me anything, right? There's no information, so I can ignore that. To react with 150 milliliters of 0.4 barium chloride. So I am faced with 150 milliliters of 0.400 molarity. Now, anytime I have a reaction, a balanced equation, you are probably using stoichiometry. Okay, and why is that? I'm starting in this unit and I'm finishing in this unit. So therefore, I need to, remember, use mole ratios using those numbers in front, which we call coefficients. So how I'm planning to tackle this is I can tell here that I can use my molarity equation. Molarity equals moles over liters. Because I have a molarity and I have a liters. So let's go ahead and do that. So my molarity is 0.400 molarity. And this is, again, of BaCl2. And I'm going to convert that to 1.5 liters. Remember, it has to be in liters. And I can go ahead and solve for moles of my BaCl2, which is what I need to use a mole ratio. I end up multiplying 0.4 times 0.5. Excuse me, 0.4 times 1.5. And when I multiply that, I end up getting 0.6 moles of BaCl2. But that's not what I need. I need silver chloride. So I'm going to go ahead and dive into a mole ratio. We did this in our last chapter. And now how do I get the numbers for the mole ratio? I use my coefficients. So the 2 came from here, and the 1 came from in front of the BaCl if there's nothing. So this is what's going to get me to moles. Now I'm actually, instead of stopping to solve, since I need it in grams, I'm actually going to take it one step further. Since I'm in moles of AgCl, I'm going to go moles to grams of AgCl. So I might as well just put it all together. So I'm going to go ahead and get the molar mass of 1 silver and 1 chlorine. And when I get that, I found it to be 143.32 grams. So to solve for this problem, I'm going to go ahead and take 0.6 times 2 times 143.32. My answer ends up being, rounded to sig figs, 172 grams of silver chloride. Okay? So that is using molarity and stoichiometry together. So you're always going to be faced with something you can solve for moles, dive into a mole ratio, and then finish off in whatever unit you need. I provided us another example here, and I provided some molar masses. I do not believe you need this one, but I think I put it there just to be safe. So if you'd like, go ahead and pause the video and try yourself to do this, and I'm going to go ahead and work on it as well. So I have 25.0 milliliters of NaOH. It's 0.35 molar. Are added to copper sulfate. That didn't tell me anything, so I can ignore that. How many grams of copper hydroxide am I going to yield or create? So same issue here. I'm going to go ahead and solve for moles, starting with my equation. So that is 0.350 molarity, 0.025 liters. I just converted that to liters. Please don't forget that. And this is of the NaOH. I can go ahead and multiply both sides by that number on the bottom, 0.025, and I end up getting 0.00875 moles of NaOH. Now, I'm in moles of NaOH, and I need to go to moles of something else in my balanced equation, so I can go ahead and do a mole ratio. Moles of NaOH to moles of CuOH2. That is a 1-to-2 ratio. Again, I got those numbers from here and from no number here, which is an assumed 1. Then I want to finish off like I did before, grams, moles to grams of the copper hydroxide. And I provided you with that molar mass right down here. So go ahead and take 0.00875, divide by 2, get an answer, multiply by 97.6, and my answer is 0.427 grams of CuOH2. My molar mass ended up being a tiny bit different than that, not very much different, just a few extra decimals, so my answer may be a little different than yours. Okay? Thanks so much for listening.